on oscillations. This is for section 3.6 in the textbook, and section 3.6 in the text looks at circuit theory and oscillations in circuits. I'm going to do the same thing. I'm going to do the same use of complex variables, but I'm going to do it for a mechanical system. So if you look on YouTube for a simple harmonic oscillator or forced spring mass system or just spring mass system, you'll find lots of videos of theory, which will duplicate some of what I'm going to do here. But you'll also find videos of spring mass systems, actual ones that are bouncing. Here I've got a diagram. This is supposed to be a solid wall, and this thing is not a resistor. This is supposed to be a spring. So you imagine that the spring is at its neutral position when x equals 0. X measures the displacement of this mass in this direction. It's a conventional sort of diagram, and that doesn't really look much like a spring, but there it is. Anyway, this mass has mass m, and it's supposed to roll freely on these rollers in a horizontal movement, and the spring has spring constant k. So the physics of the motion is really simple. The mass times the acceleration is equal to the force, good old F equals ma. So the mass times acceleration is m times the second derivative of x. And the force is the negative of k times x, because as we extend the spring, the force pulls it backwards. So that's Hooke's law. We're assuming that this is a linear spring. You pull it a certain amount, the force is simply proportional to the extension. And so when we take this term over onto this side of the equation, we get mx double dot plus kx equals 0. I've left a space here for a damping term, which I'll put in a moment. Now, if we divide this whole equation by m, we get x double dot plus k divided by m times x equals 0. And the k over m plays the role of omega squared. Omega is the natural frequency of oscillation. So this thing, if you stretched it out a little bit and let it bounce, its natural frequency of oscillation would be omega. And the spring constant is often not known, although the mass is known. So the way they find the spring constant is they set things oscillating, and then they measure the natural frequency, and then they deduce what the spring constant was. Anyway, this is the ordinary harmonic oscillator, and we don't need complex variables to solve it. What happens, though, is we often have not just a simple oscillating system that oscillates freely, is we have some kind of widget on the thing that's forcing the oscillation. So I'm not going to draw this in any reasonable way, but we'll assume that we've got something jammed into this thing and pulling back and forth on the mass with some force times a cosine of omega t back and forth this way. So we're forcing the oscillation of this spring mass system. So we're pulling on it with this frequency, but the natural frequency might be different. So instead of 0 over here, we actually have to add a forcing term. And at this point, it's already simpler to use complex variables to solve this system. It's especially nice, though, if instead of just having a spring mass system, we also have some kind of viscous damping. So actual systems, if you bump them, the oscillation will decay over time and it'll come to rest. The energy is dissipated by friction and other things. And one standard way to model that is to add a linear damping term. So it's just simply proportional to the velocity. This is very unrealistic physically, but it's actually very sensible in terms of the mathematics. This is actually an easy system to solve mathematically. Now, when I divide by m, things get a little bit more complicated in here with C over M, and I'm going to show you how to do the non-dimensionalization. So if we divide everything by M now, we get x double dot plus, and I'm going to write it in a funny way. I'm going to say C over M is 2 zeta omega times x dot plus omega squared x, and I'm going to say F cosine capital omega t here. So this thing must be equal to C over M. So that tells me what zeta is. 2 zeta omega is equal to C over M. So therefore, the damping coefficient, the factor 2 makes life simpler later, is just C over 2 M omega. So this is the equation that we're going to solve using complex variables. So little f, of course, is big F over M. So this is the equation we're going to solve using complex variables. And just as for the electric circuit case, the trick is we're going to say this cosine term is the real part of complex exponential. And we're going to force the oscillator with a complex exponential term, and the solution to that is going to be easier than if we forced it with a cosine, and then we'll take the real part of the answer. So that's the whole idea of section 3.6 for electric circuits, and here we're using it for a mechanical